you all for being here. I will tell you now all the work done during my 3 years of the PhD journey. My PhD has been developed within the framework of 2 different projects, both related with the electrodynamic tethers technology. In the first one, supported by ESA, it consisted on the development of a bare photovoltaic tether system. And then for the second one, the ETPAC-F, that I'm pretty sure that Gassem will speak later pretty much about this project. My work was focused on building a hardware emulator of the tether technology. So I will first start mentioning the state of the art of both topics, and I will present later the results of each of them. The electrodynamic tethers technology are a concept to use the surrounding plasma or to move on a spacecraft without making the use of any propellant. They make this with an electric current, and thanks to the magnetosphere of the Earth, it generates a Lorentz force that makes able to move the spacecraft without using any propellant. It was first suggested in 1996, and then this concept started evolving with the bare tether technology. This is important because the tether performance, the performance of the tether depends on different parameters that I will go through. First of them, it depends on the position of the orbit, on the Earth magnetic field, as well as the plasma density. This is important because the bare tether concept that was proposed in 1993 uses the electrons of the upper layers of the atmosphere to generate this current. Also, it is important the technology, because we need to close the circuit. We are collecting electrons. We close the circuit by emitting these electron bags to the atmosphere, so we need an electron emitter. This is the other parameter that the tether performance depends. And then we have, obviously, the tether length. So there has been some other missions that have been on the space equipped with tethers, but testing this tether, because I didn't mention it before, but they are relatively long, in the order of kilometers long meter conductors. It's very difficult to test them before going to space. So that's why we need an electrical emulator of the tether to test that it works with the rest of the avionics of the system. And only a few of them did dedicated tests on the conditioning electronics, and it is very important for the ETPAC project because it's not a very long tether. So when you're speaking with this conditioning electronics that interface the tether with the electronics of the satellite, we can lose some power, and the performance is not that good. So that's the main motivation to develop first the theoretical model of the bare photovoltaic tethers, and then building the equivalent hardware emulator of a bare tether without the photovoltaic part. So this is the concept of the bare photovoltaic tether that consists on the previously mentioned in the literature bare segment, which is the left side, plus the new addition that is the right one. These are the equations, and then when we include this new segment, we have to deal with some other parameters that differ on the tether. The boundary condition of the systems are the same, but now we have the extra constraint at which this equation need to match at the center where these segments meet. So, as I was saying before, there are some parameters, the ambient parameters, the plasma density, the motion electric field, the tether length, that determine the performance of the tether. But now, with this new implementation, new parameters that are those in the purple boxes appear as a design parameters of the system. And it's easier said than done, but when we speak about the solutions of the system, including a new segment on the tether determines the behavior not only on a single state of the tether, but around the orbit. So if we fix, because when we launch this system, we fix the tether length and the electron emitting technology, but we are suffering the variations of the ambient conditions. So in a single orbit, we can observe 4 different scenarios with this new tether technology. We investigated that, and we observed that depending on the regime, the behavior that we obtained was different. So let's now move to the second part, which is a hardware emulator of the tether. Additionally, we developed with Sener, which is a partner of the ETPACF project, we developed an electric ground support equipment to test all the avionics, and we include an electrical ground support equipment for the tether. And I will now focus only on this second part. And as I was saying before, this system will consist on the electrodynamic tether, the electron emitter, which for the TPACF it will be a hollow cathode, and we will build this hardware simulator based on this topic. We are sure that we are using the same formalism as with the bare tether, because we can always say that the bare photovoltaic tether has a 0 photovoltaic segment. But now we have the benefits of including this photovoltaic segment, which is the extra power. So this tether emulator will mimic the tether behavior on space. And in order to do that, we develop an open loop system that consists on modifying here on the satellite electronics the power. We increase it and we reduce it in both directions. We make a read of this voltage difference, and then the tether system behaves accordingly. In addition, we also change the tether ambient condition to fulfill the mission requirements. And from this study, we first observed that for our mission of the ETPACF project, we require 5 watts of extra power. So Sener designed all the electronic based on these results. And also we observed some thermal management that was required for the tether emulator. We also observed that the IV curves of this emulator match the theory of the tether system. Plus, we developed the power mode tests. As I was saying before, in both directions, we ingested power in 5 different steps. You can see them in this graph. They were 5 volts steps, and you can also observe quite well match of the theory here. And we also included some resistors within the range of 0 to 300 ohms, and it confirms as well the power regulation for the power electronics module. And regarding the achievements, each of these parts led to a journal publication, both in Acta Astronautica. And yeah, now I'm working on the thesis redaction, and that's all from my side.